Alright. Hi guys, this is the video on assignment number 4 in ECON0010. This will be going over questions 7, 8, 13 and 14, I believe. And yeah, let's get started right away. Obviously, again, disclaimer, I'm not perfect. These answers aren't technically perfect. Just a fair warning. Okay? Okay. So, let's start off with 7. We want to find the general solution of the difference equation. Now, in order to find a general solution, we need to combine the particular solution and the complementary solution. Okay? The particular solution is generally capital YT. Sorry, the authorities are outside my window. And then we've got ZT, which is the complementary solution. The complementary solution is sort of, if it was a homogeneous solution, that's what it would be. And the particular solution, we're essentially going to sub in a certain form and then find a value that works for that. So as you can sort of see here, let me enlarge my document here. You can see that we have, at the end, 3 plus 2t. So I'm going to put my particular form in a constant plus constant t. Okay? We're going to sub this into our difference equation. Okay? So you can see that we put in, in place of y, we're going to put in a plus b and stuff like that. And then the t plus 2 or the t plus 1 is going to go in place of that t there. Okay. After all that, what we get is a different expression with, instead of constants as starters, we have our a's and b's for our coefficients. And then just equating the coefficients, we get our values. So for this case here, we've got a particular solution of the form 2 plus t. Okay. If you look through the document in the description, you'll be able to see this in a bit more detail and a bit more explanation. We also want to think about the homogeneous solution. Now, we want to treat this as its sort of own quadratic. So if we have the quadratic x squared minus 5x plus 6, that's clearly got the solutions of 2 and 3. So we just get those and we're done, pretty much. How we represent those is zt is equal to, zt is the mark for the complementary solution, a, the constant, but capital A this time, and then 2 to the t. And then we'll have 3 to the t for the second one. And that's going to be our complementary solution. So combining these two, we get the general solution, which is A, 2t, B, 3t, plus t plus 2. It could be plus 2 plus t as well. So whatever you guys feel is right. Anyway, let's go into the next one. So we've got a matrix here. So we want to find, first of all, we need to find the eigenvalues and eigenvectors. Now, as you guys probably know, you find eigenvalues by essentially minusing lambda from the top of the diagonal terms, and then finding the determinant, setting it equal to 0. So in this case, we have eigenvalues of -1 and 2. What this gives us is that we sub them back into our matrix, okay, and then we times that matrix by x and y. So if I could, no, I don't really have a marker. Never mind. Yeah, actually, let me get my whiteboard up here. Whiteboard, there it is. So, how we would do it. Ignore that. That's something else. So, in order to get the eigenvalues, first of all, we would need to do the determinant of 3 minus lambda minus 1, 4 minus 2 minus lambda, okay? And so the determinant of this is going to be 3 minus lambda minus 2 minus lambda minus 1 minus 4, minus 1 and 4. In this we get minus 6 minus 3 lambda plus 2 lambda plus lambda squared. And then in this, it's going to be -5 plus that, so we go plus 5. No, sorry, not 5, dear me. 4. What this ends up being is lambda squared, dear me, minus lambda minus 2. Okay? And we get lambda values of, and this set equal to 0 gives us lambda values of -1 and 2. Now, taking note of those values there, we sub them back in. Okay? And then we get the matrices of, so for 1, we would get 2, we get 4, -1, 4, and then -1 again.
Then we basically do a times with x and y, and we get the equations 4x minus y and 4x minus y. Okay? For this, it's pretty simple to see that you can get... Hold on, let me just check what I got here. It says I got minus 4. Oh no, I must have done something wrong here. Was it 1, 1 I got with this? Or was it 1, 4? No, it was 1, 4, yeah. And this is going to be equal to 0. Yeah, so we can see from both that y is equal to 4x. Oh, that was stupid of me. So x must be 4 times less than y. So y must be 4, x must be 1. So we would get 1, 4 out of that. Okay? Then, accordingly, for the second one, we would get the matrix 1, negative 1, 4, negative 4, which gives you, at the end of the day, x minus y, 4x minus 4y, which surprisingly enough means that both will have to be equal to each other, which gives us the vector 1, 1. Okay, and that's how we get our eigenvalues and eigenvectors. Okay, now, notably, for our big question, we need to find the general solution of the difference equation and the general solution of the differential equation. So these are two quite similar parts. Pretty much all you have to do is sub it into a formula. So for the formula for the difference equation is denoted here. Hold on. Yeah, it is denoted that. So what you need to do is put your eigenvalues to the power of t, then a constant, which could just be demarked by c1 or c2, then your eigenvector. So as you can see here, I've got negative 1, it's constant, which undivided still, and then the corresponding eigenvector, which I got, which was 1, 4. And then I've got it again for 2 and 1, 1. Similarly, but slightly differently, we're going to do the same for the second one, but instead of doing minus 1 to the power of t, we do e to the power of negative 1t and e to the power of 2t. So instead of putting our eigenvalues just by themselves to the power of t, they're going to be the powers of e instead. Otherwise, it's mostly unchanged. Anyway, that's the basic questions done. Let's move on to question 13. Okay. Now, question 13 is a bit tricky. Okay, but that's all right. So first of all, Taylor's theorem. Okay, I assume you guys know Taylor's theorem. I did do further maths, so I'm not entirely sure if it was covered in A-level maths. Sort of everything sort of bleeds in and out. But I'm pretty sure you guys would know it now. Okay, so to approximate this value, we need to essentially generate a approximation for the function x to the power of a third around 8. This is the formula. And so using this formula up to, as it say here, first 3 terms around that, we can generate a equation. Now, I won't take you guys through the calculation steps. I don't think you're that dumb. Actually, that's a bit prescriptive. So all you have to do here is basically just insert the value of a, 8, into the function. So you would get essentially, yeah, you would essentially just get the value there. So that's going to be 2 for the first one. Then you're going to differentiate the function and then insert it again. And then you'll eventually get a function that looks like this. 2 plus 12th, x plus minus 8, minus 1 over 288, bracket x minus 8 squared. So that's your function. Now, how we approximate 9 to the power of a third is we just insert 9 into that function. Okay? From this, all the values are just essentially going to be 1. So we're going to do 2 plus a half minus 1 over 288. And what we get is we get 2.079861 reoccurring. And that has an error term that is less than 4,000. Now, how you get the error term is this formula. It is f. So essentially one higher derivative. So because we've done a quadratic derivative here, we're going to use the cubic derivative. So f derived 3 times, and we're going to insert the value of 8 into that. And then we're also going to do the 1 factorial higher, so it's 3 factorial. But instead of doing, we're essentially going to just do the error term, which is just one more increase. So as you can see here, if you sort of look in more detail, I don't know how detailed you guys can see it, but if you can sort of see there, it's going to be the other term. If we insert 9 into that, we get the error term, as quite a small value, as you can see here. And if we put that value under 1, you could actually calculate it as 1 over 4,147.2, which of course is less than 1,400. So there you go. Now, for the integral, we have a t times e to the it. Now, this is going to be a complex question because it's about complex numbers, not because it's like complex. So we, first of all, I assume you guys know how to integrate. So we're just going to integrate this normally. We integrate this via integration by parts, and you should eventually get the result of e to the it brackets 1 minus it. Okay? Now, we can also express this as when we put in our values, we also get, essentially we get a value on the left side like that. But you have to note that e to the power of half pi I is going to be I. Okay? If you guys remember sort of the, how do I put this? It's the polar form, I think. This is in polar form of a coordinate. So because E, that is the polar form, it corresponds to a 90-degree turn of a one, basically a line of length 1. So it will essentially turn from lying just on 1 to lying on I on the complex plane. So it's going to turn into I. So we'll have I times minus I, which becomes minus I squared, which is just plus 1. So we just added a half. So it becomes I plus a half, and then in the last one we get minus 1. And so we end up with that answer. Now, you don't actually have to calculate anything for the second one, because if you can obviously see there's a different, the difference between these two is that you've got e to the it and sine t. Now, what's notable here is that e to the it is the polar form of a complex number, and sine t is the complex part of that polar form. Okay? So all that we have to consider really is just the complex part of our answer. Now, if you can see here, the complex part just has a value of 1. So if you compute this, it will give you a value of 1. Okay? We can actually see this if you guys would like to see it. Ignore that, that's for the later question. New? Oh, you guys are so boring. Can I generate a new one? Oh, just do it like this, yeah. So if we want to generate t cos and t sine, it'll show it here. So let's generate this quickly. So if this will work, give me a moment. There it is. So for the non-complex part, we get t cos. Well, it doesn't do t cos t. No, it only recognizes x. It's not particularly nice. So that's the real part and how it moves. And then doing the complex part, we get this. Now, if we do the integral for the real part from 0 to pi over 2, we can see that that integral has a value of 0.5707. This here, pi over 2 minus 1, shockingly enough, has a value of 0.5707. So we can see that that is verifiable. But what's notable here is that if we do it for the complex parts, G0, am I doing it right? I can't even see it. Yeah, pi over 2, we can see that the value is 1. So it is that. All right? You're essentially just considering the real part of the complex part separately. Okay. Now, for question 14, we have a nonlinear system. Okay? So, to derive the linearization of the system, okay, the linearization of the system should look something like this. So you should have the Jacobian or Jacobian or something like that. But the Jacobian matrix is just the first two, I think you guys know, but it's going to be essentially the partial derivative of the first with respect to its two variables, and then the partial derivative of the second with respect to its two variables. So that's going to be the Jacobian. And the result, which we denote as z dot, which is just the linearization result, is going to be equal to I think it's ax or az, something like that. Let me check. It's somewhere in my book. Is it like somewhere here? Oh well. My books are falling down. But you essentially, yeah, hold on, let me show. So we essentially get AZ minus AZ, and we call this that. So that is going to be the linearization of the system, where XY, well, Z actually here represents the vector XY, and Z star, or Z asterisk, represents the particular part, basically the particular point you're putting into the system. So we're going to do that there. So phrasing the entire thing, okay, we essentially get this Jacobian matrix times XY, and then minus the same thing times X star, Y star, and that's the linearization, pretty much. So the solution parts, notably of this linearization, which was also said somewhere in the book, maybe it is in like the phase space area. Hold on, just give me a second here. Yeah. So if you guys, it's in nonlinear systems. Look from page 641 onwards, and the linearization of the system is gained on, yeah, it's on page 644. So we also need to note that the solution parts of the nonlinear system, okay, it wants to know here in the question, under what circumstances are the solution parts of the nonlinear system close to that of the linearization? It's close to the linearization, and you can see this on page 644, when the eigenvalue has no zero real part, okay? So then it will be close to the linearized system, okay? All right? If the eigenvalue has no zero real part, then it's good. Otherwise, you want to check again. So we're now given the particular system, okay? So for this particular system, we define our derivatives, and then we're going to calculate fixed points by essentially setting both equations equal to each other and equal to 0. You should get 4 fixed points out of this. This is going to be 0, 0, 1.50, 0, 1.5, and 1, 1. And I will show you it through this one. So as you can see, no, don't clear it. Oh, I did clear it. Cool. Love when I do that. Okay. Is it just going to be minus x minus y equals 0? Did I do that right? I did not. Screw me, I guess. Hold on, let me do this again. Oh, the thing's right there. Hold on. So it's going to be... why is it? No, it's 0. 0 is equal to x, 3x, minus 2x, minus y. So that's the first one. And then 0 is also equal to y is equal to y bracket 3 minus 2y minus x. And there we go. So if we zoom in, we can see that I've done something wrong. Oh, there is no x there. Pardon me. There we go. Right. So we can see that the intersections here form 0, 0, 1, 1, 0, 1.5, and 1.50. And those are our fixed points. Okay? Now, in order to determine the nature of these fixed points, you need to determine what their eigenvalues of the Jacobian matrix are. So calculating the Jacobian matrix, or Jacobian matrix, I don't fucking know. Oh, I need to capitalize J. Capitalizing all the J's in the Jacobian matrix. Yep. So what we get is 3 minus 4x minus y minus x minus y and 3 minus 4y minus x. Okay. So that's our Jacobian matrix. What we get in terms of individual, you basically have to calculate the matrix for each one of the points that you've got. So putting in our points, you get 3, 0, 0, 3 for 0, 0. You get minus 3, minus 5, 0, 1.5 for 1.50. You get 1.50 minus 1.5 minus 3 for 0, 1.5. And for 1, 1, you get negative 2, negative 1, negative 1, negative 2. Okay? Now, it also denotes what you can get from this. Hold on, let me do the eigenvalues. So if you get the eigenvalues from this, you should also get, you should get 3, 3 for the first one, minus 3, 3 over 2 for the second one. You should get the same for the third, because it's essentially the same. And then you should get minus 3, minus 1 for the fourth. Now, if you want to know what these eigenvalues mean, look at page 644 again. But essentially, we can see from the first one that both of them are positive, right? Both the eigenvalues are positive. If you look at the proposition B on page 644, it says if both eigenvalues of this matrix have a positive real part, no solution of our linearization for which z equals the actual particular thing we put in, it'll never approach that. So at 0, it's never really going to approach it. Okay? So we know that. All right? Then we also have, for the next two, because they have the same eigenvalues, we can do them together, they have opposite signs. Now, if they have opposite signs, then we generally call it a saddle, or a local saddle, pretty much, because, we cannot, basically, it's going to be sort of on a branch of it, where we don't really know if it's going to actually hit there or not. So it's currently at what we consider a saddle point. Now, for the final one, they both are negative, but what's notable, now, if it was just negative, then we would just call it a local stable point, okay? Yeah, it's just locally stable, but actually this is globally stable. Now, if you look at if you look at what's globally stable, it'll be on page 645 and 646. There are two conditions that have to be met out of a possible 3. The first one is necessary, and the two are one has to be fulfilled. So we can see, first of all, that both our eigenvalues are negative. That's one condition. But we also have a thing that says if the trace is less than 0 and the determinant is more than 0, then that fulfills a condition for global stability. Both diagonal entries being negative is the other condition as well, out of the 2 optional ones. Okay, so because we can see that not only are our eigenvalues both negative, but we have a trace of -4. Just for context here, a trace is just the sum of the diagonal values in the matrix. So we have -2 and -2, so the trace is -4. So our trace is -4, and our determinant is 3. Okay, so we have determinant of 3, which fulfills the first requirement, and we also have both diagonal entries being negative. Okay, I said 3 here. That was a mistake. Okay. So because all those conditions are fulfilled, we say it is a globally stable point. Not a locally stable, but it's globally stable instead. So that's generally how you would do it. Okay. Now, hope you guys found that helpful. Obviously, my workings will be in the description. If you guys need any more help, feel free to let me know. And yeah, have a nice day. Bye.